In this video, we'll look at how to get information from the graph of a function. We'll look at domain and range from a graph, we'll look at increasing and decreasing intervals on a graph of a function, and we'll look at local maxima and minima. Suppose we have the graph of f. This is some section of the graph of the function f. Recall too that the domain is the set of all inputs for a function, and the range is the set of all outputs. And the actual curve of the graph is all of the outputs. So those are all of the f of x, all the y values. Remember that we can write f of x as y just as easily as we can like x squared, right? So these, all the values on the curve are all of the y values of the function. So if we're looking at this specific interval, to find the domain, we just have to look at all of the places where this specific curve is defined. So in this case, it's like from right here, do some dashes, to right about here. We could call these x1 and x2. So the domain of this specific function would be from x1 to x2 inclusive, since we have these closed circles at the ends of the curve f. The range would be all of the values that the function f takes on from x1 to x2. Specifically, it's the range from smallest to largest. So similarly, we have all of those values there. So the range, remember, smallest to largest. So it's not just beginning to end, it's smallest to largest. So the largest actually occurs somewhere between x1 and x2. So formally, the domain and range of a function y equals f of x can be obtained from a graph of f as shown in the figure below. The domain is the set of all x values for which f is defined, and the range is the corresponding y values. So I've drawn this diagram so you can see it's basically the same as what was above, but it makes it a little bit clearer. The domain, all the x values from here to here, and the range is all of the y values, the outputs of f of x, from here to here. Now suppose we have a different graph, a graph of a function g. So this one's a little bit different. It's moving a little bit more than our first graph. And it's often useful for us to be able to identify when a function is increasing and when it is decreasing. So take a look at this graph for just a moment, and let's see if you can identify on what intervals this function g is increasing and what intervals it's decreasing. All right, so at this point you've probably noticed that from here to about here, the y value of g, the output of g, continues to increase. And then from here to here, the y value begins to decrease. And lastly, here to here, it increases again. We don't have information on this graph for x values less than a or x values greater than d, but we have enough information to discuss a little bit what's going on. So we could say that the graph is increasing on the interval a less than x less than b. And in general, will not include the kind of turning points, right? If we look at where b is, that's actually a bit of a turning point between where it stops increasing and begins to decrease. So in general, we'll have like this, a to b. Our graph is decreasing on the interval b less than x less than c. In other words, in interval notation, b to c. And then our graph is again increasing on the interval c less than x less than d. And then we have no information again, greater than d or less than a. So formally, f is increasing on an interval I if f of x1 is less than x2 when x1 is less than x2 in I. So just to get a sense of what that means, take a look at this graph, the first one on the left here. If we compare y values of subsequent x values, the corresponding y value of subsequent x values, we can see that f of x2 is definitely bigger than f of x1. So that's what we mean by increasing. If for example, we subtracted f of x1 from f of x2, we should get something greater than or equal to 0. Then f is decreasing on an interval I if f of x1 is greater than f of x2 when x1 is less than x2 in the interval I. So now take a look at the second diagram to the right. Similar idea. For two x values, x1 and x2, f of x2 is less than f of x1. So if you subtracted f of x1 from f of x2, you should get something less than or equal to 0. Suppose that we've got g of x equals x squared. We're pretty familiar with what this looks like, so I'll just mock that up real quick. So we know that at 0, at x equals 0, g of x equals 0. At 1, g of x equals 1. At 2, g of x equals 4. 3, g of x equals 9. And then the same corresponding values for the negative x's, like right about here. So a parabola looks like this. It's not a perfect parabola, but you get the idea. So now let's take a look at this. It's often useful to be able to identify when a function reaches minima and maxima, that is, minimums on the graph. We could have a kind of more complicated graph if we wanted to. Maybe this is more interesting. But the key being is that we can see by looking at g of x equals x squared that the parabola is at a minimum right there when x equals 0. And on this second graph to the right, we've got a local maximum here, a local minimum here, and another local maximum here. And this is just to say that when we compare x values, there's one that's absolutely the maximum for a small region here, absolutely the minimum for a small region here, absolute maximum for a small region there. Local maxima and minima of a function. 1, the function value f of a is a local maximum of f if f of a is greater than or equal to f of x when x is near a. When this is the case, we say that f has a local maximum at x equals a. So when I say when x is near a, really what I just mean is what I was saying a moment ago. If we compare x values close to where we think there's a maximum, like if we say that we looked at a point here, this f of x, we call that f of x1, is definitely less than this f of a. That's all that we mean. If we compare x values close to x equals a, where we think there's a maximum, the values proximate to x equals a will be less than f of a. And similarly, the function value f of a is a local minimum of f if f of a is less than or equal to f of x for x close to a. In this case, we say that f has a local minimum at x equals a. So same idea. If we compare function values close to where we think there's a minimum, those will be greater than where the minimum actually is.